For the remainder of the year, we're going to start looking at electricity. We break that into two chapters. First, electrostatics, where we talk about, as you see here, charge, force, and field caused by electricity. The second thing we'll talk about will be circuits, and circuits is the flow of electric charge. So we'll try to go a little faster through electrostatics so we have a little more time for circuits because I think that's more interesting to most students. But you have to talk first about charge before you should really talk about the flow of charge in circuits. So we'll go through this relatively quickly, but the first thing you need to know, and some of this I know you already know, but it's just the basics, that there's two kinds of charge. There's positive and negative. You already knew that. Likes repel. Unlike charges attract, opposites attract, so you already knew that. A few properties of electric charge. The first thing that you should know is electric charge is quantized, so it's always a multiple of some amount of charge, and that amount of charge is actually the charge of an electron. So all amounts of charge, if you divide them by the charge of one electron, you get a whole number, which is kind of cool. So you can't have something that is worth the value of 1.5 electrons. It's going to be some whole number of electrons. That charge is always measured in coulombs. Coulomb being the name of a scientist who did a lot of work in the field of electricity and static electricity specifically. So that's why that's kind of a funny word. Coulombs with a capital C for that. The actual variable that we use for charge is the letter Q. You can't use a C because we're using the C for coulombs. So Q for charge, C for capital C for coulombs. Again, all charge is based off of an electron, and the charge on an electron in coulombs for an electron would be negative 1.6 times 10 to the negative 19th coulombs. For a proton would be the same value, only positive. So a proton and an electron have the same amount of charge, although their masses are completely different. You can see there's 4 orders of magnitude difference between the two masses for a proton and electron. The reason I give you the masses here, besides making that contrast, is you will have a few problems in this chapter that like to refer back to universal gravitation when you talk about the amount of gravity force on something between two masses, and they'll relate that and try to draw a contrast between that and the electric force. So anyway, I just put that there as a reference for you. You won't need it in the beginning of the chapter, but since we're already talking about protons and electrons and things, there you go. The 1.6 number you will use quite a bit. So these are a reference. This you'll use a lot. If it were me, I would put this in storage in my calculator under the letter Q. If you don't remember how to do that, you can ask me in class, but that's a pretty handy thing to have instead of having to type this number in over and over because you will use that a lot. The next part is talking about how electric charge is transferred. You know that there are things that transfer electric charge well and things that don't. So a conductor is something that allows things to transfer charge easily, and that metals are generally considered good conductors because if you remember from chemistry, they have metallic bonding, in which you have the model of a sea of electrons, and that the electrons are free to flow up and down a metal. So you'll see a lot of charge sketches in this chapter. This isn't meant to be like a sketch of an atom, so don't think about it like that. It's really kind of an overall excess charge sketch. So here we're trying to look at, for every positive charge there's a negative charge, but they're not necessarily connected. The negatives can kind of flow up and down. The opposite of that then is the insulator. So in an insulator, the electrons are tightly bound to the nucleus, so the electrons can't move from nucleus to nucleus, but they can move around around a nucleus, just not transferring between them. So nonmetals are considered good insulators. The way that we sketch that's different is instead of having the minuses kind of floating around, every minus is attached to a plus. And here you see that they circled them. You don't necessarily have to circle them, but that's a common way to represent that they're bound. So they're just kind of, in whatever position, but for every positive proton you have a negative electron there. So that's what that sketch shows. So conductors and insulators. So how you can transfer charge, we'll look at 3 basic ways. The first thing is charging by contact. That should be simple enough. That's just touching. In charging by contact, there's really two ways that you can do this. One is by friction. Friction is a really good way for charging insulators specifically. I think the easiest thing to think about is like the rubber, if you do like a balloon and rub it on your head. Here they have like a ruler with a paper towel. I don't know how often you do that, but a lot of people when they play with balloons like to play with a charge on it. So there's actually a cute little diagram from this off of the PhET website. So if I take a balloon and I rub it on a sweater, I'm basically ripping the electrons off of the sweater, and then you can see they're attracted because I have a positive side of the sweater and a negative balloon. In this, they'll even let me add a wall. That's pretty exciting. So if I do a wall, if I have this negative charge and it comes near the wall, you see the negatives don't want to be near it, so they'll try to get away if they can. So that's the whole basis of what we're looking at in statics, is how charges behave when they're close to each other. So charging by friction is just kind of the rubbing thing. The second one is charging by conduction. So on this one, conduction meaning basically just touching. Usually you think about this when you're charging conductors, which would be metals for most cases. So if you take something like this diagram, you have something that is charged and something that is neutral. When you touch them together, the charge is just going to float between the two. So let's say, I didn't count these, let's say there were 20 charges here. When they touch, there would be 10 on each if they were going to be that specific. So the charge would spread equally between the two, and then when they separate, then those charges would repel each other and be passed around equally around this sphere. So you can see on this one there, that's why they're kind of spread out a little further here. They're trying to repel the other positive charges. But once they're apart, they just repel equally and they kind of scatter about and do their thing. So conduction is basically a way to share charge. So if you're going to charge something by conduction, if you have something positive, you're going to end up with something that's going to be positive at the end. If you start with something negative, it's going to be overall negative at the end. It is important to note, however, one thing that's probably not perfect with this diagram is we always consider the negative charge to be the charge carrier. The electron is the mobile part of the electron. So it's the electron that's doing the moving, not the proton. So when you see these diagrams, don't think about those as necessarily protons per se, but they're trying to talk about areas of overall charge. So an overall positive charge and then the movement of that overall positive charge isn't really trying to say that the protons are moving. It's really the electrons that do the moving, but that's just kind of how they diagram it. So hopefully that's relatively clear for you. The next way that you can transfer is by induction. Induction is a little more complicated than the last one because it's not just, conduction was just touching, right? The first one. So on this one, induction is more of a process, and I'll show you this here as we go. On your notes packet, you should have 3 blank bars underneath this section, and we're going to fill this in as we go. So you're going to start with something that's a neutral object. So that's supposed to be shown here by an equal number of positives and negatives scattered about, this being a conductor where they're not bound to the nucleus at all. So if I want to charge this neutral object, I'm going to charge it by induction, meaning I'm not going to actually touch the neutral object to the charged object. So I'm going to have my neutral object, and in this case I'm going to use a negative rod. The same thing would work, by the way, with a positive rod. But when I bring a negative rod near it without touching it, the negatives inside the neutral object are going to be repelled by that. So they're going to kind of come over here to the right. Now, if I were to move this rod right now, these negatives would go back over and float away and look just like it did at the beginning, and it'd be still a neutral object. So I need to do something in order to change the overall charge of the object. What I'm going to do here that's different is I'm going to add a ground to the situation. So here's my same situation as before, except I add a ground. A ground is basically, think about if you think about a lightning rod attached to a house, and if lightning hits a house, all that extra charge from the lightning goes directly into the ground. The ground isn't really affected because the earth is so large, a small amount of charge one way or the other doesn't affect the earth. So the same thing happens here. Usually if you ground something, you think about connecting it to say like a pipe or something like that that's long and can handle a lot of charge, something that's conductive like a pipe. Sometimes you can actually just do it with your finger. It depends on if it's a small amount of charge, and let the let the extra charge go into you. You wouldn't want to do that with like lightning, but you could do that with like a balloon, something that isn't going to hurt you. So that's what we do here. We ground the object. That basically gives us a way for charge to, in this case, go out. If I had used a positive rod instead, think about this. If the rod were positive, then all my negatives would be over on this side. And then if I were to ground it, then electrons would come in and fill in this spot, which would be all positive by itself. So there's a difference between the two. So in this case, I'm doing the negative rod, and I'm basically pushing out the negatives through the ground. Okay, so now if I get rid of both the rod and the ground, what's left over is a positively charged object. So in essence, what happened is I took a neutral object, I used a negatively charged object to leave it with a positive charge overall. Again, the same thing could happen if I had a positive rod. I could make this a negative charge. So that's a contrast to the last type that we talked about on induction. You're going to be charged, if you charge something by induction, it's going to end up with the opposite charge of what you're charging with. As opposed to when you charge by conduction, it was the same. So that's one thing that's different. There is a video that has like a lot of explanation on induction, and that's posted on the website. It's a little bit painful, a little bit sleepy, but it actually explains it really well. Look for the creepy face about 4 seconds in. That's kind of entertaining. But very good explanation on the charging by induction if it was a little fuzzy for you here. So the third one and the final one is charging by polarization. Polarization, basically you're just taking something that is an insulator, and we said that there are plus and minus sides to any particular atom here, but they can basically rotate. So the minus is going to stay with the plus, but the actual alignment of the atom can rotate around. Think about, actually let's think about like water being a polar molecule. So if this were water, sometimes I do this in class where I'll take a little stream of water and take a balloon next to it, and the water will actually bend as a result of the charged balloon being next to it. The same thing happens here where we have a positively charged object and the negative charges of this insulator are going to line up with the positive. So if this were a negatively charged object, then it would flip and you'd have the positives on the inside and the negatives on the outside. When you charge something by polarization, this is temporary. As soon as this charged object leaves, then the insulator would go back and rotate, however. So that is it for the beginning of charge. We'll start looking at the math in the next section with Coulomb's law.